Now the chapter which we are going to start is chemical equilibrium. This is one very basic chapter, but it's still highly important. The reason for that is that this makes the base for another chapter, ionic equilibrium, which is highly important and has got lot of weightage in any competitive examination. In this case, what happens? What is equilibrium? First of all, understand this part, that part only. Actually, in equilibrium, there are basically two types. One is called static equilibrium. Static equilibrium. Other one is called dynamic equilibrium. Static equilibrium, I'll give an example. You might have seen seesaw. So what happens in seesaw with which children play? We will have like this. One person sits here, other person sits here, and if both have got exactly same weight, at that time this comes in equilibrium. This doesn't move. Although this is the point which is balancing heat here, so still the total this bench gets balanced and nobody moves. This is static equilibrium. In certain cases like chemical equilibrium, what happens that if A is converting into B, then B again converts into A. This type of equilibrium is known as dynamic equilibrium. In chemistry, we get only dynamic equilibrium. Here, what happens that if we have got two reactants A and B, they are reacting with each other and give certain compound C and D. Under normal reactions, what happens? We make only one arrow like this, and this shows that the reaction proceeds only in one direction. Only A and B can react and produce C and D. But in case of equilibrium, what happens that even the products, in this case the products will be C and D, even they can react and give back A and B. This is the sign of equilibrium, that A and B are giving C and D, while C and D react back to give A and B. This is called equilibrium here, and as I am telling you that the reaction keeps on going, A and B give C and D give back A and B, so this becomes a dynamic equilibrium. Now, if we go for law of mass action, which was given by Gullberg and Waage, two scientists, then according to law of mass action, rate of a reaction is equal to proportional to product of concentration of reactants, concentration of A into concentration of B, raised to some powers, and if the reaction is elementary, then the powers become the same as stoichiometric coefficients. We assume here that the stoichiometric coefficients are A, B, C and D. The small ones are stoichiometric coefficients, while the capital ones are reactants and products. Now, with the help of this law of mass action, I am trying to find rate of forward reaction. This is RRF, here rate of forward reaction. This becomes proportional to A, stoichiometric coefficient is A, so power becomes A. This is B, it becomes power B here. We remove sign of proportion, so we get a proportionality constant. We assume the proportionality constant is Kf here. So, rate law for the forward reaction becomes the rate of reaction Rf equal to Kf into concentration of A raised to power A into concentration of B raised to power B. This becomes rate of forward reaction. Now, similarly, what happens here, as soon as C and D are produced, they too start reacting and give back A and B. If we want rate of backward reaction, then again by law of mass action, we will give it as the rate of backward reaction equal to Kb, we assume to be rate constant for this one, into concentration of C power C into concentration of D power D. Now see, I will give some introduction about Kf and Kb here. They came here as proportionality constant. These proportionality constants Kf and Kb are known as rate constants. Kf here is rate constant for the forward reaction, while Kb is rate constant for the backward reaction. Remember, rate constant depends only and only upon two factors, one being temperature, other one being catalyst. If you change temperature, value of rate constant changes. Similarly, if you add some catalyst into the reaction, again value of rate constant changes. Remember one thing, you change anything else, you change concentration, you change moles, you change volumes, pressure, anything else is changed, rate constant does not change, it remains constant. Okay, now, so this is Kf and Kb, depend only upon two factors, temperature, number two, catalyst. Now, in the beginning, suppose we started this equilibrium process in a container. In a container, we took A and B. You can assume to be gases, you can assume them to be liquids, whatever you want right now. We are not bothered about that. We started in a container by taking certain amounts of A and B. In the beginning, the rate of forward reaction is going to be maximum. You can understand easily because concentration of A and B will be maximum in the beginning. Now what happens that A and B react and produce C and D. As soon as C and D are produced, they too start reacting and give back A and B. When they are giving back A and B in the beginning, the rate of reaction is going to be minimum. You can understand again, in the beginning C and D concentrations will be minimum. If it is minimum, this is rate law is proportional, rate of reaction is proportional, the rate of reaction also backward reaction will be minimum. As time passes, concentration of A and B decreases while the concentration of C and D increases. As a result, rate of forward reaction keeps on decreasing slowly, while rate of backward reaction slowly keeps on increasing. At one moment, rate of forward reaction becomes exactly equal to rate of backward reaction. This point in the system is known as equilibrium point. Okay, this how we can give, this can be given as, we get rate of forward reaction, at equilibrium we get rate of forward reaction as rate of backward reaction. We substitute the values here, this becomes Kf into concentration of A power A into concentration of reactant B power B, we get equal to, which is Kb into concentration of C power C into D power D. Simple substitution we do here, we get Kf by Kb and it becomes equal to concentration of C power C D power D upon concentration of A power A into B power B, right. Kf and Kb, again you remember these are constants, so their ratio also will remain constant. So we put a constant here, K. This K only is known as equilibrium constant. So from here you can understand that equilibrium constant is nothing but the ratio of rate constants of forward and backward reactions. Now we get K as equal to concentration of C power C into D power D upon A power A and B power B. This is the expression for equilibrium constant. One thing again you should understand here, that this is a dynamic equilibrium. No reaction has stopped. Although both the reactions means finally the system has come to constancy, means concentrations of C, D, A and B have become constant, but the reaction has not stopped. So the concentrations are not changing. Why? That whatever amount of C and D is produced, in the same time exactly same amount is converted back into A and B. Same thing happens with A and B also, that whatever amount of A and B decomposes, exactly same amount in same time is produced by C and D. As a result, although the reactions are proceeding still, but concentrations become constant. This is known as dynamic equilibrium. Equilibrium constants, depending upon what we use for using the equilibrium constant, may be mainly of two types. I'll tell you which two types they are. Suppose A, B, C, D are in gaseous state. We assume they are in gaseous state. These are in gaseous state. If I write their concentrations, then it becomes equal to concentration of C power C into D power D upon A power A and B power B, like this we get here. In this case, if I am using equilibrium constant, if I am writing equilibrium constant using concentration terms, like in this case we have done, then the equilibrium constant is known as Kc. Now, because all these are gases and we assume them to be ideal gases, we can use PV equal to nRT. Now, obviously, when the reaction is happening, we assume the temperature remains constant. We can say here that if temperature is constant, this is universal gas constant, we get P proportional to N by V. Now, N by V is nothing but number of moles by volume of container. So, this becomes concentration of the gas, which becomes proportional to partial pressure of the gas. So, concentration of the gas will be proportional to partial pressure of the gas. We substitute it here, means concentrations we are writing in terms of partial pressures. If we write it in terms of partial pressures, then the same expression becomes partial pressure of gas C raised to power C into D raised to power D upon partial pressure of A power A into partial pressure of B power B, right. This equilibrium expression has been written in terms of partial pressures. So, this expression is called now as Kp, like this. Means if you are writing equilibrium expression using concentration terms, it is called Kc. If you are writing equilibrium expression using pressure terms, it is called Kp. There is one more expression of equilibrium which is written in terms of mole fractions. Means what we do there, we write a mole fraction of C into mole fraction of D upon mole fraction of A into mole fraction of B raised to powers, respective stoichiometric coefficients. This type of equilibrium constant is usually denoted by Kx. Usually it is not used that much, but sometimes it may be required. Now, we can correlate Kc and Kp also with each other. How? Going to show you that one. See. For this expression, we are writing Kp. Now, we are going to establish a relation in Kc and Kp. Both are equilibrium constants using different terms. Kp, as I told you, using partial pressures of the gases, Kc using their concentrations. We are going to establish a relation in Kc and Kp now. See, we write Kp for this expression, and if we write Kp for this equilibrium expression, then Kp will be equal to partial pressure of C raised to power C into D power D upon partial pressure of gas A raised to power A into partial pressure of B raised to power B. As I told you, we have got ideal gas equation which says PV equal to nRT. Okay, so we have here P as equal to nRT by V. Same thing we are going to substitute here, and we get, after substituting it here, we get PC means partial pressure of C equal to number of moles of C into RT upon V raised to power C whole into partial pressure of D, which will be given as number of moles of D into RT by V again raised to whole power D upon partial pressure of A, which will be given from here as number of moles of A into RT by V raised to power A into number of moles of B, sorry, pressure of B, which will be NB into RT by V whole raised to power B. Like this we get here. If you notice here that RT by V is common in for all of them, we take here NC by V, ND by V, NA by V and NB by V here, then it becomes, we get Kp as equal to NC by V power A, sorry, C power C into ND by V power D upon NA power A, NA power V raised to power A into NB power V raised to power B. Here we take this RT by RT as common and this becomes into whole RT whole power, we get C plus D minus A plus B. Okay, simple mathematics here, nothing new, nothing more complicated here. If you notice, this term is nothing but equilibrium constant using concentration terms. Why? Because this is nothing but concentration of C power C upon, sorry, into concentration of D power D upon concentration of A power A into concentration of B power B into RT power C plus D minus A plus B. Right or no? Now, if you notice, this is nothing but Kc. Previously we have shown how Kc is written using concentration terms. So simply we can write it as equal to Kc into RT. Now see, this is Kp equal to Kc into RT. If you notice, this is nothing but number of moles, stoichiometric coefficients of products minus stoichiometric coefficients of reactants. Okay, and actually one more thing you should understand, that this we can write as delta N, but RT whole power delta N, this is difference in number of moles of products minus reactants. But remember, this delta N must be taken only and only of gases. If any liquid or solid term is there, that must not be written here. So we get it as delta N G. Means we get the relation as Kp equal to Kc into RT power delta N gaseous. One of the important relations of equilibrium. Very important relation.